Okay, good morning. Today's lesson is actually very short. I realized there is one missing thing that I haven't covered in the previous lesson about geometric progressions. I want to complete it and then I will give you time to practice on your own if you want to. So, so if you remember last time we talked about a geometric progression. A geometric progression is a sequence of numbers so that each term is obtained from the previous term by multiplying it by a constant number. That constant number is called the common ratio and it is denoted by R. And then we had two main formulas for the geometric progression. One was what is the nth term. The nth term was a1 multiplied by the common ratio r to the power of 1 unit less. That was the formula. And we also found the formula for the sum of n terms. Yes. So that was a1, 1 minus r to power n divided by 1 minus r. A1 is the first term, r is the common ratio. I told you that in some books they multiply the numerator and the denominator by minus sign, and they will get actually a1 r to the n minus 1 divided by r minus 1. So it doesn't matter. I myself prefer to use the first one, which is also written in your book. So something that is interesting when it comes to geometric progressions is that what happens if I want to add the terms, but infinitely many of them? Might be the first impression is that, okay, there is no point for that. If I add infinitely many numbers, the answer will be infinite. That is right when you're dealing with arithmetic progressions, yes? So in an arithmetic progression, let me just deviate a little bit. For the time being, pretend that this is an arithmetic progression and you want to calculate Sn. The formula in Sn for arithmetic progression was something like this. Yes? It was a1 plus an, but I wrote it in that way as well. So now you see that what happens when I start increasing the value of n, a1 and d are fixed numbers for my arithmetic progression. I cannot change them in the middle. What I can change is the value for n. So for example, if I add the first 10 terms, n is 10. If I add the first 100 terms, then the n is 10, is 100. So hopefully you agree with me, by starting increasing the value of n, always and always this sum will increase. Yes? Of course, increase means in magnitude, because if I have negative value for d, I will have a decreasing sequence, and then it eventually becomes negative. And if I add negative numbers, it becomes a huge negative number. So when I say it becomes big, I mean from magnitude point of view. So in principle, if you want to write it more formally, you say the limit of this sum Sn when n goes to infinity, okay, when n approaches to infinity, is either infinity plus infinity or negative infinity. So this is positive infinity if d is positive. It is negative infinity if d is negative. Yes? Is that clear? Because if d is positive, when I increase n, this becomes a huge positive number. Compared to that huge positive number, this constant number is negligible, and you are still multiplying it by a huge number. So it becomes a huge positive number. If d is negative, when I increase n, this becomes a huge positive number, but when you multiply a huge positive number by a negative number, it becomes a huge negative number. And then this one becomes a huge negative number, this is a huge positive number, so if you multiply that, it becomes a huge negative number, which is minus infinity. So for the case of arithmetic progression, we didn't have this topic. We didn't have this lesson that what happens if there are infinitely many terms that I want to add them up, because the answer is always infinity or negative infinity, depending on the sign of the common difference. You might think that is also the case for geometric progression. I don't know, do you have any idea? So if I have a geometric progression, by the way, the terms in the geometric progression even grow faster, yes? But they grow faster if r is what? Can you tell me? So for example, if I want to have an increasing sequence, an increasing geometric progression, what should be the property for R? I mean, R can be 1, which is not interesting at all, because if you start multiplying any term by 1, you will generate the same thing. So R equals to 1, even though technically is right, but usually we exclude that because it will generate the same number over and over again. So let us forget about R equals to 1. Let me limit ourselves between two cases. Okay? Or between 0 and 1, or greater than 1. If R is greater than 1, what is your intuition? What your intuition tells you about the sum when the number of terms becomes very big? For example, R greater than 1. Let me choose R to be 2. And let me start from somewhere, say 2. Let me start from 3, okay? I multiply it by 2, the next term is 6. I multiply it by 2, the next term is 12. Multiply it by 2, 24. And then this list will continue. You see that when R is greater than 1, I am facing an increasing sequence. Now, what is your intuition? If I add infinitely many of these numbers in this list, what is your intuition about the sum? Yes? It is positive infinity. So because these numbers are getting bigger and bigger and bigger, and if I add infinitely many of them, it is not very strange to see that this is infinity. By the way, can we have a better idea why this is infinity? The answer is yes, because as I did for the case of arithmetic progression, I can use the formula for the geometric progression for this case. So let us calculate Sn for n terms. A1 is 3, 1 minus r, which is 2, to the power of n, divided by 1 minus r. But 1 minus 2 is minus 1. I use that minus 1 to flip these two. So then it becomes 3 times 2 to the power of n minus 1. This is the formula for Sn. Now I ask you, what is your intuition about the limit of Sn when n goes to infinity? What is that? I am making n a huge positive number. When n is a huge positive number, 2 to that power becomes a huge number. And then minus 1 is a huge number, multiplied by 3 is still a huge positive number, so it's positive infinity. There's nothing interesting on that. But now let us change the idea, and instead of taking r equals to 2, let me limit myself to this situation, yes? Then what will happen? For example, instead of choosing r to be 2, let me choose r to be 1/2. And still I start from the first term 3, but of course the next term is 3 over 2, because this time I have to multiply that by 1/2. So what happens next? Then it becomes this. This is a little bit counterintuitive, because still the numbers are positive numbers. Of course, they are getting smaller and smaller. But the question is that what happens if I add infinitely many of these numbers? Of course, each term will contribute much less than the previous case, but at least it is not negative. I am adding something to the previous. For example, if I consider the first term, it is 3. If I consider the first and the second one and add them, it is 3 plus 3 over 2, which is increasing. If I consider 3 of them and add them, of course, it is being increased all the time, every time, yes? I agree with you that these numbers are getting smaller and smaller, so the number that I am adding every time becomes smaller and smaller. But that is one thing clear. I am adding something to the previous term, yes? And I have infinitely many of these additions. So might be the intuition is again that, okay, it grows again to infinity, but much slower. Okay, but the intuition is not that. So you see that the intuition is that when I add infinitely of them, it becomes a number. Okay, so that is what we want to discuss today. So let us just answer this question for this sum. First of all, I just calculate Sn for any arbitrary n. How should I calculate that? Using the formula. The formula here. A1 is still 3, and then I have 1 minus, or in this case is 1/2, and then I raise it to power n, then 1 minus 1/2. This is the sum. If I add n of them only, but let me simplify this a little bit. So this becomes 3, this becomes 1 minus. 1 to power n is 1, 2 to power n is 2 to the n, and then in the denominator, 1 minus 1/2 is just 1/2. Okay, and then this 1/2 in the denominator will go in the numerator, so Sn is finally 6 times 1 minus 1 over 2 to the n. Okay, now I want to do the same thing. I want to take the limit of this Sn to see what happens if I increase n to infinitely large values. Okay, so what is your guess? What is happening? I am increasing n. When I increase n, 2 to the power of n increases. But the numerator is a constant. When the denominator increases, every time I am dividing 1 by a bigger and bigger number. So when I send n to infinity, the denominator becomes infinitely large, and when I divide 1 by an infinitely large number, nothing is left. So the limit is 0. So the answer will be 6 times just 1, which is 6. Of course, we will not achieve 6, because to achieve number 6, we have to really add infinitely many of these terms. But this is something clear. This is a little bit counterintuitive. So in this case, you see that if I start adding them up, even though there are infinitely many numbers involved, but the limit reaches to 6. If I do it infinitely many times. Of course, if I do it billions of times, billions of billions of billions of times, I will come closer and closer and closer to 6. But I will not go beyond that. Yes? So that is what we just, actually I described. So in a general context, we can write a formula for it, yes? So can you tell me what can I write for the formula? I want to write something similar to this. But this was very boring because this was always the case, the same numbers for arithmetic progression. But for geometric progression, we can say that the limit, okay, can you tell me what should I write? The limit of Sn is equal to two cases. If r is what? Between, so let me write it, r greater than 1, what happens for the limit? What happens? Yes? What type of infinity it matters, yes? Because if you go here in this formula, if r is greater than 1, when I raise it to an infinitely large power, it becomes positive infinity. But 1 minus positive infinity is negative infinity. But then it depends to the sign of a1. If a is positive, so it becomes negative infinity, yes? Am I right? No, sorry. It becomes positive infinity. Why is that? Because r is greater than 1, so the denominator is negative. Okay? And if n is very large, this also becomes negative infinity. Divided by negative, it becomes positive infinity. So if a1 is positive, it becomes positive infinity. Yes? But then, if r is greater than 1, but a1 is negative, it becomes negative infinity. So these are the boring ones, comparable to the case of arithmetic progression. But there is something interesting for the case of geometric progression, and that is what happens if R is between 0 and 1. Okay, what happens if R is between 0 and 1 and you raise it to higher power, you are making it smaller and smaller, yes? If I have a number which is between 0 and 1, when I raise it to higher powers, I am not making it bigger, I am making it smaller, yes? So if I raise it to infinitely large power, then nothing will be left from this term. So it will be 1 times A1 divided by 1 minus R, always. Okay, so that was missing from my lesson last time. I saw that this is also in the book. So if you have a geometric sum, for example, they might write something like this. Sigma 3 over 2 to the power of n plus 1, for example, and then they say n goes from 0 to infinity. So you want to understand this sum. So whenever you see that you have infinity on top, remember there's only one scenario for you. They are asking something about geometric progression. Because other one, except those things, except this, you haven't studied this before. So whenever you have a sigma with infinite on top, so it means that probably you are facing a geometric progression with infinitely many terms. Okay, so what we do, first of all, you really need to convince you that this is a geometric sum. How should I convince myself? I will start expanding the sigma a little bit, yes? So I would say that the question mark is equal. Instead of n, I put 0. I get this. Instead of n, I put 1. I get 3 to the power of 2 to the 2. Instead of n, I put 2. It becomes 3 to the power divided by 2 to the power of 3. And then I continue this list. What I have done, I have just tried to expand the sigma to see the situation better. But do you agree with me this is a geometric sum? How should I know that? Because I need to compare each term with the previous term. So what is happening? What is happening that I can go from here to here? This term is being multiplied by 1/2. And then exactly the same thing happens here. From here to here, the term is multiplied by 1/2. So this is really true that this is a geometric sum. Okay? When it is a geometric sum, it means that I need to talk about Sn here, but because there are infinitely many terms, either every time, I don't know if this formula is in the formula sheet or not, but anyway, you need to understand when r is between 0 and 1, when you raise it to infinite, that part becomes 0. So that is you need to know. So if you have this formula in the formula sheet, definitely you have this one, but when r is between 0 and 1, you just ignore that term, so what is left is a1 over 1 minus r. So you need to understand that this sum that is written is actually a geometric sum. For the geometric sum, you need to understand what is r in this problem. In this problem, r is 1/2, because every time I am multiplying things by 1/2. And I need a1. Reading a1 is also very simple. A1 is 3 over 2. So then you write that in front. 1 minus r, and then the numerator is a1. Exactly this form. So then it becomes 3 over 2 divided by 1 over 2, and you simplify it, it becomes 3. So that is interesting. So it means that if you are patient, of course this is not possible, if you add all these terms, the answer that you will get is exactly 3. Any questions? So by this lesson is now complete. Okay, so you can start working on all those exercises. Any questions? Okay, I will update the Google Classroom, and if you have any questions, you can ask me.